Okay, so I think we're going to start. So we're going to start by making a differentiation between learning and memory. We typically, the chapter on this topic is typically learning and memory, and some people conflate learning and memory, but there's actually a subtle difference. So learning is basically the process of acquiring, taking in new information. So when you encounter an event, how you benefit from this new information. Memory is the ability to actually store this information and retrieve that information should you be interrogated for that information, whether it's via recall or recognition or some sort of way to recall the information. Now, sometimes you think you did not learn something, but sometimes it's just the problem of how the memory was interrogated for that information. Meaning that if you provide the right retrieval cue, you might actually get to that information. Okay? Now, we know that damage to certain areas in the brain can seriously get at your memory and maybe abolish certain types of memories. We also know from research on patients like H.M. Henry Molaison, who now we know his name because he's dead, but for the longest time he was called H.M. So for many, many years when I taught about him, I would say H.M. Not his name. But then I believe in 2008, he died. And this guy suffered from some serious amnesia, where he could not learn any new information. And he lost a little bit of the information that was right before the accident. Okay? So, and it's because of patient HM that we learned that memory is not this homogeneous phenomena. It's not like there's only one type of memory. Okay? I don't know if you remember, like in the old movies, somebody gets hit over the head and then like they lose their memory. Do you remember that? Okay, you're okay. Thought you were too young to remember that, but maybe not. Okay, so, and then like they would lose them. So I was always, as a child, when I saw movies like that, I was like, okay, so do they forget how to drive? Do they forget the alphabet? How come they still remember certain aspects? How come they don't? And then now we know, because of patients like HM, who has contributed so much to our understanding of memory, he doesn't know how much he's contributed to that field. We know that memory, there are different types of memories. And we know that different types of memories are different because they're represented by different parts in the brain. Okay, so first let's make a general differentiation between what's called retrograde amnesia and anterograde amnesia. Retro means like in the past, yeah? So retrograde amnesia is going to be the loss of memories that are formed in the past, before the actual onset of the amnesia. Okay? Kind of like losing the past. Henry's old memories, at least the very old ones, not the ones that were right before his surgery, were pretty much intact. So he didn't have retrograde amnesia. He had a little bit of retrograde amnesia, but really his very old, distant memories were intact. Okay? He had a severe disability, though, in remembering in the future, so forming any kind of new memories, what's called anterograde amnesia. So post his surgery, he couldn't remember anything. So his doctor in Montreal, Canada, her name was Brenda Milner, every time she would see him for the 40 years, she has to reintroduce herself. Okay. Do you remember that movie, what is it, 50 First Dates? Kind of like that. Okay? So what happened to Henry that led to this inability to form new memories? So he had severe epilepsy and seizures. And these seizures were kind of circumscribed to the hippocampus. So the doctors decided to remove both hippocampi, one on the right and the one on the left. Okay. And sure enough, when the doctor removed both hippocampi, his seizures were alleviated, so he had way less seizures per day. His intelligence, in fact, went up a little bit, okay, and he seemed fine. His mental abilities, other than memory, were fine. But then what was severely affected was his memory, that he couldn't remember, he couldn't form any new information. But it's not like he couldn't remember any information. There was some sort of information that he could remember, but others that he couldn't. So, for example, in a task called the mirror reverse text, so where you have on the mirror you have reverse text and you read it, usually with practice people get better. Well, the same thing with him, that with practice he got better, meaning that he did benefit from this practice. There was some memory component to that. But when you ask him, do you remember doing this task? Do you remember that we have practiced this 100 times? He'd be like, this is the first time I do this task. I don't know what you're talking about. It must have been like luck that I got to do this. And who are you, by the way? Okay, so here's the hippocampus, which looks actually like a seahorse. It has a very distinctive shape. And in fact, a big portion of my dissertation for my PhD was just on the hippocampus and the different parts and contributions to different memories. Okay. The hippocampus is embedded in a part that's called the medial temporal lobe. So we talked generally about the lobes before, and temporal lobe was one of them. This is the medial portion of the temporal lobe that we've talked about before. Okay. So if we look at the slides here of somebody who's normal, a brain scan, and HM, what you notice where the red circles are is that there is a hippocampus in the normal subject and that area is empty or black in HM. Can you see that? Okay, in the top. Okay, and also, so another task that he got better at with time, just like normal controls, is that you look in the mirror and you draw what you see in the mirror, which is reversed. But you can't look down at the actual drawing. And with time, people got better, and same thing with HM. He did get better as well. Meaning that he can actually, there's some sort of learning that he can acquire, that this anterograde amnesia didn't hit everything, all types of learning. And also, more significantly, is that there are different types of learning. There are all different types of memories. Okay, so here's the reversed, mirror reverse text. Can anyone read that? Okay, go ahead, Vin. Go ahead, read.
Me?
Yeah.
If you practice reading text that is mirror reversed, you will become better and better at
Deciphering
the text quickly.
Mm-hmm.
This is an example of learning of perceptual skill.
Good, I didn't even get that word. Okay, good. Perceptual skill, okay.
It does not require an intact hippocampus.
Yeah, yeah. Okay. Well, if HM had a problem with the hippocampus, it was removed, and he can acquire this task. This also tells us that the hippocampus is not needed for this task, or that this type of memory is independent of the hippocampus. Okay. Okay. So let's even divide or subdivide memory even more than that. So there's two different categories of memories. There's what's called declarative, and then the opposite of that would be non-declarative memory. Declarative memory is memory that you're conscious of reporting it, conscious of remembering it, things like facts or information or what questions. So when I give you, if I give you a surprise quiz right now, the information I would be demanding would be declarative memory. or the information in the test, that will be declarative memory. Who's the President of the United States, that will be declarative memory. So that kind of information, okay? We're actually aware of processing it. Non-declarative, sometimes called procedural memory, is memory that's shown not by declaring the information, but by performing the information, by showing that you know it. So answering, for example, how questions. Okay? Okay, learning to drive your car. You're not really conscious of, well, I need to press on the gas, I need to do this on the brake. You're actually just doing it without awareness, kind of, without like deliberate consciousness of remembering the information. Okay? So long-term memory, memory that's there for years, you have the declarative and the non-declarative. And declarative memory can be tested very easily in humans because you can give you a test and say, what have you learned? And Henry Molaison was unable to form any new declarative memories. But the very old memories were fine. The very old declarative memories was fine, relatively speaking. So what does that mean? What does it mean that Henry Molaison, who had his hippocampi removed, was able to form some declarative memories, or not form declarative memories for new information, but some of the old declarative memories were sure enough fine? What does that mean?
The hippocampus is a way to form new memories?
Exactly. That it could be potentially that the old information that's from long time ago, declarative information, is stored elsewhere, not in the hippocampus, or becomes over time independent of the hippocampus. But the formation of new declarative memory, sure enough, depends heavily on the hippocampus. Does that make sense? Okay. Now, non-declarative memory, declarative memory it's kind of hard to measure in animals. So when you do experimentation in animals, it's hard to give an animal a test and say, what test? Answer this what question. So it's a little bit tricky to do that in animals. Non-declarative memory, that where you test it by showing, or the person shows you that they know something, or by performance, is a little bit easier to test in animals, and obviously in humans. Now, Henry could form this type of memory fine. Okay? Which tells us that skill learning, or procedural memory, or non-declarative memory, is somewhat hippocampus independent. The storing of it and the formation of it is hippocampal independent. Does that make sense? Does the logic? Okay, so, but we do sometimes need to test declarative memory in animals because we want to be in control of removing the hippocampus and seeing what happens in the animal, or removing different parts. And that is, you can't do that in humans. You can't say, you know what, we're going to do the study, half the group, we're going to remove a portion of their brain to see how it affects memory, with compensations will be allocated accordingly, with maximum compensation for death. You can't really do that because that's unethical, obviously. Okay, so we had to come up with creative ways to test declarative memory in animals. So one such task is what's called the delayed non-matching to sample task. Okay? And this is a test of object recognition, typically done in monkeys, to have them declare what they know, to basically answer what questions, okay, in a clever way without obviously having them talk. Okay? So basically what happens is the monkey sees an object, and then the monkey is rewarded that after a delay, they see this object again and another object. They are rewarded for picking the non-matching object. That's why it's called non-matching to sample. Which requires that they remember the old object, that they've seen it before, memory component, and selecting against that to get their reward. Okay? Now we know from this research that the medial temporal lobe, where again the hippocampus is a big part of it, is crucial for this task. Okay, so here's a picture of the monkey. The monkey sees this key, and then you have some sort of delay in seconds or up to minutes. And then you have a test where you have two objects, and the monkey is rewarded for picking the object that was not seen before, that did not match the sample. Now, the longer the delay between the sample and the test, the more severe the impairment if the monkey has a medial temporal lobe damage. So maybe a monkey with medial temporal lobe damage can get away with a very short delay and do this task successfully, but as the delay gets longer and longer, the monkey can't do it. Because then the medial temporal lobe becomes important for that type of learning. Okay. So here, hypothesis is that we know that some parts of the temporal lobe, the medial ones, are going to be very important for the formation of new information, or the acquiring of new information. So how do we test that? We move different parts of the temporal lobe from both sides of the brain, because if you only do it on one side, well, maybe the other side is compensating. Okay? So because if you remove one hippocampus, you don't get the severe impairment in memory, because then you have another hippocampus doing the job. Okay, so you move different parts and you see, and then you test the monkey and you see if the declarative memory is affected until you get to a part where when you take that part out, the monkey cannot do the delays and non-matching the sample task. Okay? And what we know from removing different parts of the medial temporal lobe, so, and let me go over which parts are in the medial temporal lobe other than the hippocampus, which we talked about. There is a part that's called the entorhinal cortex, another that's called the parahippocampal cortex. Para means around, hippocampus, parahippocampal cortex, and the perirhinal cortex. So the perirhinal and the entorhinal cortex are the anterior parts, or the front parts, of the medial temporal lobe. And the parahippocampal cortex is a bit on the posterior side. Okay? So on the y-axis, you have a memory score on the task that we talked about, on the declarative task that we talked about. And then we compare different groups to the control group that has both that has the medial temporal lobe on both sides of the brain intact. So what happens if we only take the hippocampus out, or lesion only the hippocampus? The memory score is reduced a little bit, but not tremendously. Okay? However, if you take lesion the entorhinal cortex and the parahippocampal cortices, which is the, I guess, the mustard colored bar, you see a further reduction in the memory score. If you take out the entire medial temporal lobe, including the entorhinal cortex, the perirhinal cortex, the hippocampus, you see in the red bar, like no memory at all, or like the animal loses the ability to do this task. Okay? So for this task, for this type of declarative memory, the more of the medial temporal lobe that's left intact, the better the performance on this task. Can everyone see that? Okay, which is this conclusion here. Okay. We have another patient called NA who has amnesia, but because of damage elsewhere, not really in the medial temporal lobe, in the dorsomedial thalamus, so in a nucleus in the thalamus that's called the dorsomedial, and the mammillary body, which really connects them to the hippocampus. And because of this damage in the mammillary body, which really connects with the hippocampus, that loss of connection with the hippocampus, like Henry Molaison, NA has short memories, okay, so just like the monkey with short delays, the monkey can do the task. But as long-term memory is interrogated, declarative formation of new memories he can't do that. And he cannot do that task. Okay? So very similar symptoms to HM. Okay. There's also what's called Korsakoff syndrome, which is basically a memory or a deficiency that is as a result of a severe deficiency in vitamin D. Okay? Which is, I want to say, almost synonymous with or happens because of chronic alcoholism, where the person develops severe amnesia for acquiring new declarative memories. Okay? And the brain damage there hits the mammillary bodies and the dorsomedial thalamus, but not the hippocampus. But what's kind of fun about these patients is not only that they have this amnesia that where they can't form any new declarative memories, but that they can fabulate. They make up stories that are consistent with the scenario. They fill in the gaps, meaning that they're not aware that they have this amnesia or that they have this complete deficiency in forming new information. Okay, and that could have something to do with the fact that the alcohol has also led to some frontal damage as well. Okay, so the yellow arrow is pointing to the dorsomedial thalamus. Okay, and if you see here, there is no dorsomedial thalamus. And then the red is pointing to the floor of the third ventricles where the mammillary body would be, but obviously here it's black because it's gone or destroyed. Okay. So this is the brain damage in patient NA, the one we talked about earlier that had similar symptoms like HM but had different brain damage. Okay. Another patient, Casey, had this unique type of memory loss where the patient could not remember any personal memory. Okay. He had damage to pretty much a lot of the cortex, the anterior part, the back part, and Casey had no problem, I don't want to say no problem, I mean, it did have to be a lot of training to form semantic information. So semantic information is information that's not personal. So for example, if I ask you, who was the president before Obama, you can recall that information, but you might not remember the one instance where you actually learned this information. Okay? That's like semantic information. It's declarative memory that's like not personal. If I ask you what typically happens at birthdays, he would say you get a birthday party, and you know, you get a beating, whatever that's typical of a birthday party. At least we used to anyway. And that's semantic information. But if I say what happened at your 19th party, that becomes personal information. So patient KC lost or couldn't remember any personal information. But with a lot of training, though, not easily, Casey had no problem learning new semantic information. Unlike patient HM, Henry. Henry couldn't do that, in addition to the loss of the personal memory as well. And really this happens when you have extensive damage to the frontal, parietal area, to the right parietal occipital cortex, and shrinkage in the hippocampus and near. So a lot of shrinkage and a lot of damage pretty much all over the brain. Okay. So again, this brings up this information from, so each patient kind of brought us a little bit closer to knowing tease apart the different types of information, different types of learning and memory. So this, we know now that there are two subtypes of declarative memory. Remember we talked about declarative versus non-declarative or procedural. And now I'm even saying that declarative can bifurcate into two different types. Semantic information, which is kind of like general, non-personal, declarative information. And episodic memory, which is this autobiographical, personal information, like what happened at your 19th birthday. Not generally speaking what happens at people's birthdays. That's called episodic memory. And my dissertation was on episodic memory, personal information and how it's represented in the brain. Okay. So patient KC, we said that this patient had shrinkage in the hippocampus, which explains why this patient couldn't form any new information. Okay, so that makes sense. But not the loss of autobiographical past information. Because remember we said that with patient HM, that past distant memories were fine, but just couldn't form any new information. So the KC's damage was way more pervasive than HM. Does that make sense? And I do want you to know the different patients and what the damage was and how that was manifested behaviorally. So you should keep track of that. Okay. And even in the normal subject, when you hear your own story, you have different brain activations than if you hear somebody else's story. So here in the top panel, you have brain activations that correspond to hearing your own story, okay? Which, as you can see, is very different and don't really overlap with hearing somebody else's story. Which makes sense. If you're able to say, well, yeah, actually this happened to me, that's my story, or actually this is somebody else's story, your brain has to have some sort of activation or patterns of activation that differentiates between that subjective feeling of this is my story, that's their story. And indeed it does. Can you see that? Okay. So learning a skill, which is not part of declarative memory, okay, which is something that HM can perform fine or learn this new skill fine, can be challenging for everyone, but it can be acquired through repetition. And there's different types of skill learning. So there's sensory motor, there's perceptual, there's cognitive, and we know that because HM didn't have a hippocampus, or hippocampi, I should say, one on the right, one on the left didn't have either, was able to do this fine, all these different skill learning, the sensory motor, the perceptual, the cognitive. We know that this type of learning, skill learning, is independent of the hippocampus, or does not require the hippocampus for its storage or encoding. Okay? But what we know from other patients and other studies on other areas in the brain, that an area in the brain that's crucial for this type of information is what's called the basal ganglia. Okay. So some examples of the perceptual skill learning is what you did earlier with the mirror reverse reading. That would be a perceptual skill. Cognitive would be like doing puzzles. You'll get faster at doing it if you keep doing it. And something called the Tower of Hanoi problem. You can actually play this on the website. It's pretty interesting. You should do it. You get better at it also with repetition. Okay, sensory motor. So maybe remember that star that he was tracing from the mirror without actually looking down at the drawing. That would be an example of a sensory motor, the mirror tracing, where the person gets better with repetition. All of these tasks, HM or someone with hippocampal damage can do just fine. Or can reach a level that's comparable to controls. Individuals who don't have the hippocampus damage. Okay. Another type of kind of like a repetition learning is what's called priming, which is a change in how you process the stimulus because you were exposed to that stimulus before. Okay. Victor, Say orange 10 times.
Orange, 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 orange.
What's the first vegetable that comes to mind?
An orange.
Vegetable! Vegetable picture.
You tricked me. I would say a carrot.
Exactly. Okay, I tricked you twice in that instance. So what I did here with him is I primed him with a color, and perhaps if I didn't do that, he might come up with a different vegetable. But the reason why he said carrot is because I primed him with the color orange. Yeah? This is what it's called priming. Okay, that response why he said carrot and that change in answer and how he processed my stimulus, the question, is because of priming. Because of prior exposure, where he had to say orange 10 times. Okay? Okay, so how we test this, for example, is something that's called the cued word completion. We have the patient or a subject look at a list of words. For example, stamp might be on that list. And then we can give them a test after and say, complete STA with a word that came from that list. A patient that has hippocampal damage would be like, well, I've never seen a list before, first of all. I don't know what list you're talking about, but I'm just going to complete it with something. And we'll put stamp, as opposed to start, as opposed to other words that begin with STA. Okay? There's tons of words that start with STA. So they don't remember actually learning the list, but they did benefit from seeing that list somehow by quickly choosing the word stand as opposed to start. Does that make sense? That's called priming. Yes?
So you're saying someone with hippocampal damage can do this?
Can do this.
They're just not aware that they learned.
Exactly. Exactly. So if I say to them, complete this word here, this cued word, with something that you've seen on a previous studied list, they'd look at you and be like, I don't know what list you're talking about. And if you're like, just complete it with the first word that comes to mind, they'll say stand. Even though it's just as frequent as the word start. So they're more likely to complete these cued word completions with words that have been seen before. So again, this is a way that you're benefiting from experience. This is a type of memory. Okay? So this type of memory is going to be also independent of the hippocampus. But it also happens to be also independent of the basal ganglia. So remember we talked about skill learning, perceptual, cognitive, sensory, motor, and we said that this type of memory or learning depends on the basal ganglia. Well, priming, which you would think would also depend on the basal ganglia, because it's kind of akin to what we talked about, it actually doesn't. But it depends on different parts of the cortex, depending on which priming you're engaged in. So perceptual priming is going to depend on some visual areas. Okay? Conceptual priming, okay, so where maybe I will prime you with a category, okay, that has to do with meaning, is going to depend on the left frontal cortex. Does that make sense? So let's say I prime you by mentioning a category of furniture. If I ask you to say the first word that comes to mind, you might come up with an item that's a furniture item. Okay. Now there's also different types of non-declarative memory. There's what's called associative learning, which actually can happen for declarative as well, which is building an association between two things or two stimuli. So the most infamous type of associative learning, or one that I'm sure you've all learned about, is called classical conditioning or Pavlovian conditioning. Okay, so you remember the dog and the tone and the meat powder, you remember all that? Okay, so where you have a neutral stimulus that on its own, the tone, is not going to elicit salivation. The dogs don't come into the world knowing to salivate to tones, right? But because this neutral stimulus was paired with another natural stimulus that typically elicits salivation, okay, like the food, the meat powder, then this natural stimulus is this neutral stimulus is no longer a neutral stimulus. It has become now conditioned or a conditioned stimulus, and now can elicit the same response as an unconditioned stimulus, the meat powder. And it's unconditioned because the dog doesn't have to learn that you salivate food. It just does. Now, through its fermentation and lesioning different parts of an animal's brain, we know that also this type of associative learning, the Pavlovian conditioning, is also hippocampal independent. But it does depend heavily on the cerebellum. Okay. Another type of conditioning or Pavlovian conditioning that's actually done in rabbits is the eye blink conditioning, where you kind of like blow a puff of air at the eyes, whether actually humans or not. And if you pair that puff of air with the sound of tone, if the sound of tone precedes that, every time you get this puff of air, you hear the sound of tone first, you start to blink to the sound of the tone, even if there's no puff of air. Okay, so this type of learning is going to depend on the cerebellum. Another type of learning is called instrumental conditioning or operant conditioning, where basically there's an association between a behavior and what happens after that behavior, or the consequences of that behavior. So if the consequences of that behavior are you get a reward, you're more likely to do that behavior again. If the consequences of that behavior is that you get a punishment, you're less likely to do that behavior again. If the consequences of that behavior is that you take something that's annoying to the person away, you're also more likely to increase the likelihood of that behavior again, what's called negative reinforcement. Okay, and this is tested in animals by putting the animal in what's called a Skinner's box, and I'm going to show you in the next slide. And really, we haven't really been successful in finding exactly the neural circuit of operant conditioning, this behavior plus consequence relationship, how it's really represented in the brain. So this is a Skinner's box where the animal is in this box, and each time they learn that each time they press a lever that they get a reward. So because they get a reward, they get food, they keep pressing the lever. Now, a few decades ago, they discovered that animals, especially like rodents, they discovered this in rodents, have what's called the cognitive map, which is kind of like a mental representation of how things are relatively related to each other in space. Okay? So let me give you an example. You know the layout of this classroom because we met tons of times in this classroom. It doesn't matter where you come through this door or that door, you're not going to get lost going to your seat. Because you have a cognitive map that knowing, well, that door in the back is close to all the flyers over there, that if you come from this door, you're not going to be next to that board. So you have this relative spatial representation of space that you're not going to get lost. Same thing with an animal. You put a rat in a maze, you change and you ask, it has to go to a certain location. It doesn't matter where you put the rodent, the rat, at the starting position of that rat. It has a spatial representation of that layout, but it doesn't matter where it begins, it's going to get to its final destination where it's going to be rewarded. Okay? As long as there are spatial cues on the laboratory wall. That's what a cognitive map means. We know that the hippocampus is extremely crucial for this type of learning or this spatial learning. In fact, we know from studies in rats that the hippocampus contains what's called place cells. Okay? These cells are going to be active when the rat is in a particular position in the environment, in a specific spatial layout. Once the rat moves away from that point, let's say place cell A is going to fire only in that location, then it's going to stop firing. And place cell B is going to fire in a different location. When the rat is in that location, then place cell B is going to fire. So that's what I mean by place cells. And it's like you really hear like the action potentials. You hear it moves away from that spot, then another place cell will fire. Okay, and then you put the rat in a new environment. These place cells remap. They come up with a new map and come up with a new representation for these place cells. Okay, that's like an incredible feat. Does that make sense? Okay. So, and then in the next slide, I'll show you a picture of an 8-armed radial maze, where typically we test spatial location in rats. The rat must recognize and enter the arm that they have recently visited to get a reward. And if you have a lesion in the hippocampus, the rat can't do this. It produces a spatial deficit. Okay? If it's only a motor kind of task, and you damage the hippocampus, the rat can do that. What do I mean by a motor task? Is, so let's say, for example, so a rat that has an intact hippocampus is going to do a layout, is going to have a cognitive map of a layout of this area, of this maze. So let's say that there happens to be a clock on top of the most recent visited arm. The rat, doesn't matter where the rat begins, they know that they have to go close to that area where the clock is, because they have a spatial map. It doesn't matter if they begin here and they have to go to the right, or if they begin here and they have to go to the left. In a motor task, the animal gets rewarded for always going to the right position. Okay? So it's going to really depend where they start. If they start here, they go to the right, it's the most recent visited area. If they start over there and they go to the right, they actually go to a very different location. Can you see the difference between the two tasks? How one is spatial and requires that the animal benefited from the learning of the spatial layout, using cues on the wall to know how to go to the recent visited area, and one that's a motor task where the animal, their task is to always go to the right. No matter where their starting position is, they're always going to the right. Okay? This motor, always go to the right, learn that go to the right, get a reward. Go to the right, get a reward. That type of behavior doesn't really require the hippocampus. But the one that benefits from all the spatial cues on the walls and the spatial layout does for sure need the hippocampus, and a lesion in the hippocampus would severely make the animal deficient in that task. Okay? The motor task, however, okay, we already said the hippocampus is not important for that one, but what is important is the basal ganglia. So here's the task. If you lesion the hippocampus, you see how there's a very low percentage of correct responses. If it's a spatial location recognition task, meaning that the animal is looking at the walls, is making a spatial layout, using these cues to guide them to which area or which arm they visited last. Does that make sense? So you see the hippocampus, the blue line here, it's way much lower than other types of lesions. So if you damage the control, which is in the green, it's fine. The basal ganglia, which is in the purple, is fine. Damaging the extrastriate cortex, all of these areas, when you damage them, you don't get the severe reduction in memory scores on this task, the spatial task, like the hippocampus. If we look at a response recognition memory task, okay, where you have always go to the right, always go to the left. You see what you see here is which area or which group has the worst score on the test. The what? The basal ganglia, exactly. The purple line. Okay? All the other types of lesions, the hippocampus, the extrastriate cortex, the controls, all of them, yes, there's a little bit of reduction in score, but the most severe is the one for the basal ganglia, where the basal ganglia is damaged. Okay? The sensory perception, okay, which is, again, a type of priming we talked about earlier, can be measured by object recognition. Does the animal recognize seeing this object or not? Okay. And we talked about one task, which is non-matching to sample task, where the animal is going to have to pick the object that does not match an earlier seen one and gets rewarded for that. This type of task also requires cortical damage as well. So here you see that the most decrement in this type of task happens for the extrastriate visual cortex. Extrastriate meaning areas outside V1 or the primary visual cortex. Now, spatial memory and hippocampal size, there's some sort of intimate relationship between spatial memory and the hippocampal size in many species. For example, birds that store food in different parts of the world and then has to go find that food when it's hungry. Imagine that you stored it in some tree, like, thousands of miles away, and you have to go find it. That requires an incredible spatial ability. Well, birds that can do this have a much larger hippocampus than birds that do not hide food. Can you see that? Okay, and this is the log scale. And this is not just for birds, this is for other species as well. So to kind of summarize what we've presented so far, that when we talk about memory, it's not like memories are stored as files in a specific file cabinet in the brain. We already talked about there are different types of memories, and because there are different types of memories, there's going to be different regions in the brain that represent the different types of memories, okay, which is the different forms of memories. They're going to rely on different brain mechanisms. And also, the same brain structure might be involved in different memories. So there might be a circuit where they overlap, they have overlapping parts to give rise to different types of memories. I like this slide a lot, and I highly recommend you really, if you really understand the slide, then you understand everything we've talked about up to this point. Okay? Because we talked about so many different ways to categorize things and divide things, and this sums it up really nicely. And also, I like the fact that it draws back arrows back to the brain regions that correlate to these areas. Okay? So we began with long-term memory, and then we said long-term memory is divided into declarative memory. What memory? Things that you can declare, things that you're conscious of, versus non-declarative or procedure memory, where you show me you know something by performing it, not by telling me. Okay? We know that declarative is very much hippocampal dependent, and that non-declarative is hippocampus independent. And we know this because patient HM that didn't have hippocampi cannot do long-term declarative new information, but can acquire new non-declarative information. And then we said that declarative memory can then further be divided into what's called episodic versus semantic memory, personal versus non-personal memory. Episodic is remembering like you are like the author of that memory. Okay, you're not telling it from some sort of like third person. Semantic is this memory doesn't have a context. So what's the capital of France? You don't remember where you actually learned this information, okay? As opposed to remembering your last visit to France. And then we said that episodic memory, over time, at the beginning, the initial formation of this episodic memory, hippocampus is crucial. But then after a long time, the representation of this memory gets stored elsewhere outside the hippocampus in the cortex. Now, I want to say that in the field, there are debates over does memory eventually become independent of the hippocampus or not, but for the purposes of this class, over time, as the memory becomes old, it gets independent of the hippocampus and gets stored in the cortex. But just in case you go on in the field, I don't want you to think I lied to you. I just want to say that there is some controversy over that arrow going from episodic to storage in the cortex. Okay? And then semantic is also going to be stored in the cortex as well. And then non-declarative or procedural, you have skill learning, like knowing how to ride your bicycle, which to me is a risk-taking activity. Priming, just like the example I gave with Victor. Okay? Conditioning, associating two stimuli, one that's typically a neutral, one that doesn't elicit any kind of response, and one that's unconditioned that indeed does elicit a response. That learning to pair the two things together, that's the cerebellum. Okay? And we humans do that too. Right? Every time you see a red light, you go. It's not like typically you were born to know, you stop. Obviously, you don't want to drive where I live. You stop when you see red light. That you didn't come into the world knowing red means stop. You learned that association. Okay? Okay. Now, a memory doesn't just jump into becoming a long-term memory. There are stages it has to go through before it becomes a long-term memory. There is what's called iconic memory, or kind of like picture memory, kind of like it's very, 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 very brief, extremely brief, but it's storing like the sensory impressions. It's as though the sensory neurons continue to fire after you've seen a certain stimulus. That after firing is what's called iconic memory. Kind of like the residual activity of sensory neurons. Now, in a couple of seconds, that goes away. That vanishes. Okay? It's kind of like, have you ever looked at a picture and then looked away at a wall, and that picture was like on the wall? You know what? So that's what I mean by iconic memory. Okay? And then there's what's called the short-term memory that lasts for a few longer seconds, maybe 30 seconds or so. But that's also kind of limited in how much information it can be in that short-term memory. So not everything in iconic memory is going to make it to short-term memory, but certain parts of iconic memory will stay in short-term memory. And there's also a related type or stage called working memory, where as long as you're working with that information, kind of it's on the back burner, but you're working with it, it's going to stay as long as you're manipulating and working with that information. For example, you parked your car this morning way more than a few seconds ago. So it's not short-term memory. But you remember where you parked it at the end of the day. Hopefully, you're going to go and find your car. Yeah? You don't sit in class and say, I parked my car third row, second car, next to the red car, and then hope the red car doesn't be before you. Right? You don't do that. Hopefully. But you end up finding your car. And then if I come next week and ask you, remember last Monday, where did you park your car? You'd be like, are you crazy? Of course I don't. So it's not long-term memory, where it's in there forever, but it's also not short-term memory, where it's only 30 seconds or less. But it's working memory. It's information that you know you're going to need it in a few hours to find your car, and then after that, it gets discarded. Okay? Now, information in short-term memory, or working memory, with rehearsal can actually go to become long-term memory, where it lasts for potentially years. So let's say, for example, that since you started here, every single Monday you park in the same spot. Every single Monday you come early enough and you park in that spot. That has now become a part of long-term memory. Then yes, maybe months after, if I ask you, you're going to be like, yeah, this is exactly where I park. Okay. Now, the capacity of long-term memory is infinite. So there's no such thing as I overloaded my brain, I studied too hard, I took in too much information, I need to delete some. You're not a computer. You're a human, you have a brain. That's a human brain. There is no memory overload. And that's what's so amazing about the brain. Okay? And again, long-term memories can be in there, but you just don't remember them because you haven't been provided with the proper retriever cue. Like, I don't know if this has ever happened to anybody where, like, you totally have forgotten about something, and then years later something happens in the environment where you're like, oh my God. You guys are laughing. You know exactly what I'm talking about. You remember a memory that happened like 20 years ago. That if somebody were to ask you, do you remember what happened, you'd be like, of course I don't remember. But some sort of retriever cue in the environment, whether it's a smell, it's somebody's scent, whatever it is, just brought on that memory. Now, the ones that are laughing, you have to tell me what memory you're thinking about. Okay. So does that make sense? Okay. So a functional memory system, a working memory system, is going to have these three processes. You're going to have an encoding kind of system, which is a system to get in the information, to enter the information. And this kind of language is borrowed from computer science. Okay? So sensory information is going to be encoding the short-term memory. Now, if nothing is done at this stage, it won't go beyond that stage, short-term memory, and it'll be lost. But if something is done to consolidate that information, then that information can actually be consolidated or moved to long-term memory. Now, there are many different ways to consolidate that information. For example, rehearsal, repeating the information, working with the information, embedding that information into an already existing scheme, going to sleep after that information. So remember in the sleep chapter we said the different stages of sleep, deep sleep versus REM sleep, are going to be important to consolidating different types of information. This is what I mean by that. And then there has to be also a way, a process in the brain that is going to be allowing for the stored information to be called upon or to be retrieved. Okay? Because otherwise, how do you know if you're encoding the information or if you actually remember the information? There has to be some sort of mechanism in the brain to correspond to your subjective, kind of like phenomenological feeling of I am remembering this information versus I'm encoding this information. So here's another good slide. You have incoming information from the environment, like listening to the lecture, looking at the slides, all that stuff. And a lot of this information is going to be in the iconic memory, which is going to last just a few seconds. But with efforts to encode this information might go to short-term memory, just a subset of this information, because the iconic memory includes overwhelmingly everything that's going on here. But imagine if you remember everything that's going on here, that would be just very overwhelming. Okay. A subset of it is going to go to short-term memory or working memory, depending on what kind of information we're talking about. And with some sort of rehearsal, some sort of method for consolidation, then that information can go back to long-term memory. Now, at any of these stages, information can be lost. So, for example, when an information is retrieved from long-term memory, once you take, you're retrieving a long-term memory information, that memory, when it comes out and you're working with it, you're remembering something, filing it back, it's not the same memory anymore. Every time you retrieve this memory, it's not going back as the same memory anymore. And that's why there's no reality. So every time you retrieve information, it becomes fragile and labile again, and has to go through reconsolidation to go back to long-term memory. Yes, Sasha?
So then, can that memory then change?
Yeah. In fact, there are certain types of therapies that do exactly that. There are certain types of therapies, for example, PTSD, post-traumatic stress disorder, where they have, let's say, the rape victim, the person who came back from war, whatever stressor they have them bring back a long-term memory, and they try to disturb that memory. Now, that kind of decision could be important, because if you're a rape victim and you want to remember this information so you can pursue the person who did this to you, that is a tough thing to do, because do you want to forget these memories? But forgetting these memories might mean that you can live a better life. So it becomes very tricky. But sometimes what they will do is they'll bring back that long-term memory, and they might do something like electric shock. Electric shock will make you forget the memory. Okay? So there's a lot of work here. Oh God, I forgot the guy who does this for PTSD. Anyways, there's like somebody who's renowned, and the name is not on the tip of my tongue, I can't lie. But anyhow, where he does this, he brings back long-term memories that are painful, and through different types of approaches, for example, electric shock will erase that memory. Okay? But then again, you might make the decision then to erase that memory, but then in the future, if you want to use it for whatever, the court system, for whatever reason, you have to think about that. Okay? So for example, people who are depressed, who are severely depressed, there is still a subset where medication is not working, nothing is working. There is still a subset that gets electric convulsive therapy. And they lose, up to maybe 2 weeks of memory prior to that session. Okay? Okay. We also know that brain mechanisms or brain representation of short-term memory and long-term memory are different. Okay? The short-term memory can be encoded, retrieved, but doesn't really require an intact hippocampus. So when you're sitting with HM, with patient Henry Molayson, as long as the doctor is talking with Henry and there's no disruptions, HM has no problem remembering that's the doctor that treats him, and no problem with that. But let's say the doctor goes to the bathroom and comes back, then Dr. Brenda will have to reintroduce herself again. So short-term memory is fine, as long as it's not interrupted. Which tells us that this type of memory is not dependent on the hippocampus. Okay? Now, the movement of this subset of information in short-term memory, consolidation of that information, to go to that long-term memory is crucially important, or the hippocampus is crucially important for that process, as we know from patient HM, Henry, and many other patients who have hippocampal damage. Is that this information cannot get past short-term memory, because the hippocampus is not intact or damaged or lesioned or something wrong with it. Okay. So which means that short-term memory is going to be a lot more vulnerable to any kind of trauma than long-term memory. So really long-term memory, especially the very distant past long-term memories, are way more secure than any recent memory. And if you remember with patient HM, I said that he couldn't form any new information, long-term information, and I'm talking obviously about declarative because we make that distinction. And he also lost some information that were just a few years before the surgery. So that's kind of evidence for information while it's getting consolidated, and maybe in humans it takes a few years, maybe 3 years, to get consolidated before it moves out of the hippocampus to the cortex. That if something happens, a motorcycle accident, a surgery to remove the hippocampus, anything that's going to happen that is going to interfere with the hippocampus, during the time it's consolidating, moving the information from short-term memory to long-term memory, is going to that information is going to be lost, in addition to the ability to form any new information. Okay, does that make sense? It's so funny though, because as a society we work in reverse. You work very hard throughout your youth, your childhood, if you are given one or not, and then you're saving up to retirement, you're saving everything, you're saving your life to retirement, your money, your ability to travel, all that. But it's really all this information or this past experiences, you're not focusing on it, and then you don't end up having a past. And this is the information that's going to remain with you if you have any sort of trauma, which hippocampus gets hit with. If you have any kind of seizure, the seizure, because of the location of the hippocampus and the type of connection of the hippocampus, it gets hit hard. And it's one of the areas that is very prone to seizures. So my friend's mother-in-law, for example, she got some sort of virus, and it hit her hippocampus, and she lost her memories. Okay, there's also what's called a primacy effect and a recency effect, and you're probably familiar with this, is that if I show you a list of words, you're more likely to remember the beginning and the end of the list than the middle of the list. Okay? Now, how about for people who are amnesic? Do they also show primacy and a recency effect? If we give them a list, do they also show higher chances of remembering the beginning and the end of the list? So here's normal adults. For primacy, on the x-axis you have the item number. So whether it was first on the list, second, third, fourth, last. And then on the y-axis you have the percentage correct. So you see that there's a primacy effect and a recency effect in the blue line for normal adults, with recency a little bit higher, okay? Because it's really close to memory. You just finished reading the list, you're going to remember the last thing. But with patients with amnesia, look at this. They don't have a primacy effect, but sure enough, the recency effect is just as good as somebody who's not amnesic. Why do you think that is? Why do you think that they don't show primacy effect or higher percentage correct for the beginning items on a list, but they do match controls in terms of percent correct for most recent items on the list? Why do you think that is? Yes, Victor.
Patients with amnesia are able to remember the items more recently said, since those items are still in their short-term memory.
Exactly. That's exactly the right answer. We already said that patients who have a hippocampal damage, that their short-term memory is fine. Well, items that are most recent on a list, just like Victor said, might still be in the stage of short-term memory. Okay? While things that were said at the beginning of the list, that might already be past short-term memory, where the hippocampus is needed to remember these initial items. Does that make sense? Okay. Also, let's look at this effect as the interval of time is longer. So with a zero delay, you get recency effect, but again, no primacy effect. With a somewhat short still delay, not a little bit longer, but not very long, you get both the recency and the primacy, okay? But after a very long delay, you have a primacy effect and no recent effect. Okay, so this is for the serial position curves, with the x-axis being first item, second item, third item, fourth item. Okay. So as I said before, long-term memory, you have a vast capacity for long-term memory, but also it's subjected to some sort of distortion, especially when it's brought back to life again through retrieval. But a subject can learn, 10,000 images of scenes and can recall them. That's enormous. Okay? Because they leave what's called a memory trace, which is basically a record laid down by some sort of experience that you have. This memory trace doesn't really deteriorate over time, but can be interfered with if you have experiences before it or after it. So an earlier experience might interfere with it, or an experience after it might also interfere with it. Okay, and again, the process of retrieving information from long-term memory can make these memories become unstable again and make these memories require reconsolidation for it to go back to long-term memory. But once you bring it back up for retrieval, you can actually interfere with this information where you can create a false memory. So there was a whole thing where a therapist would bring in patients, females, and under hypnosis would bring back memory and would basically plant in memories of sexual abuse by their fathers, where all of a sudden all these females were going to court saying that they were sexually abused by their father. And it was basically a nasty byproduct of the way this therapist was doing therapy with these female patients. Okay. I think I'm going to stop here, and we'll pick up from here next time. Any questions?